Okay, so very good afternoon. So we'll continue our discussion on some very specific instances of the accelerated gradient, sorry, the generalized gradient descent. The first one will be proximal. I already gave you an idea of what the generalization is about. The generalization is basically you're adding a non-differentiable, potentially non-differentiable component to the functions that we have been generally considering. Now, what you could do, of course, is go back to our famous subgradient descent, right, which was discussed earlier. Well, if I have a function of the form f(x plus cx), so the one option I have already in front of me is assuming cx is non-differentiable and convex. Okay, so one option I have is to consider subgradient descent. Now, is there a specific disadvantage in going for subgradient descent? Can you think of what I might miss out if I go for subgradient descent?
Descent may not be guaranteed.
Okay, so the problem is descent is a misnomer. What else is a problem?
It's not
You need a hull. Basically, you need the subdifferential and sample from that subdifferential. What else is a problem? Do you think I can get good Lipschitz properties? Can I go for acceleration? The smoothness is a problem. Anything with acceleration? See, the problem with acceleration is that you need momentum. Or the fact that descent itself is a misnomer, and that you need to go get from a hull. I mean, hull is like a big space, right? So we have already seen this. So basically, you're looking at this entire right, this entire space. So this is a space, the space of normals, and this is a space of the tangents, right? So you have to deal. You may land up with any of those points from the hull, and then velocity also becomes a challenge. So while we could potentially avail try and avail some of these properties, right? So some of these properties like the subgradient descent, can try and do Nesterov, Polyak, try and get some Lipschitz property, but you can't get smoothness. So can we do something more interesting when you have proximal, when you have a different approach altogether? So we're changing the approach. Okay? So the idea here, generalized gradient descent, generalizing subgradient for non-differentiable and constrained cases. Well, constraint is an example of non-differentiability. So this was our example. So I want to minimize fx plus cx. And this together I'm referring to as capital Fx. So obviously I want to overcome some of these problems. what could you do, right? So we already said, well, if I had to consider gradient descent, I won't be able to apply that to Cx. One way was subgradient, but here I present a slightly different option. How about I do gradient descent for f, right? And then do a retrospective correction for C. So gradient descent for f is xt plus 1 is xt minus blah, blah, blah. And then I say, well, let me look at what xt plus 1 itself means, right? So what we're trying to do is view gradient descent for fx as quadratic approximation, as minimizing, sorry, as minimizer of quadratic approximation. And then I'll try and make some changes to that quadratic approximation. So what was this? Just look at it. Xt plus 1 is a argument over x, f of xt plus 1, blah, 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 right? If you just differentiate this with respect, this is an quadratic approximation around xt, okay? So view gradient descent update. So quadratic approximation around xt using the slope as gradient of f at xt. That's what this is. I'm trying to avoid repeating whatever is on the slide, right? Of course, this had a gamma. So that is a challenge, right? And we saw a lot around how we can try and fix the gamma, or come up with a better adaptive version of gamma, right? All of that was part of Adam and Adagrad and all that. So for now, we'll kind of say, oh, there is some fix to gamma. Okay. And step size gamma. So better to list out whatever we are assuming. Okay. And we are saying that just like we're trying to address stochastic, so subgradient descent using proximal, we also have addressed gamma, addressing gamma using Adam, RMS probe, Ada delta, and so on, Ada grad, and so on, right? So we are deferring that. Say, okay, we'll stay with this gamma. And then what we'll say is, well, what is the C actually doing? So one is the F part here. What is the C really doing? What kind of C may we encounter? So one version of C is like an indicator function. So what's an indicator function? Which says, well, constraint which right ICA C could be X is that norm of X where C is less than or equal to delta, some center. Okay, so if the point goes outside, our intuition says projected back, right? Can I come up with an algorithm where for something like this, the projection becomes a natural version of the generalized gradient descent or the proximal descent, whatever name we are going to give. Okay, so I've given you 2 points, right? One is, can I do something with this quadratic approximation, generalize it? The other is, I would like this algorithm to adhere to intuition. Intuition is very important. It shouldn't just, so what is the intuition? Intuition is, if I had a constraint like this, And my iterate xt plus 1 was here. This was my C. My intuition says that I should project it back. That projection would mean, well, look at the normal, and along that normal, I should find the closest point within the set. Okay, so what could be our generalization which gives us, which is intuitive? So an intuitive alternative, what we want. We want to certainly do away with subgradient descent. Right, but an intuition is, this is intuitive. Okay, any thoughts? What could you do? How do you think we can extend this quadratic approximation and put a Cx there? So give me something that minimizes the quadratic approximation, but with a correction, with a Cx correction. Still not guaranteed that will give me something intuitive, but at least it's a leap. We are trying to we want to move away from subgradient descent. Okay, so let's consider that unless you have some better thoughts. Okay, so this is our first effort. So I put xt plus 1 as r min over x of the quadratic approximation modulo gamma around xt, all of that fine, plus a cx. Okay. So this is my intuitive alternative. Let me write it down. I don't want this. You can write this expression down. Okay. Now question is, does it make sense? Right? Anyways, we can also do the following. We can try and simplify it. So what's the simplification? R min over x. Does f of xt hold any value when I'm doing an r min over x? This part is constant. What else can I do? My favorite, can I do something with respect to completing squares, right? So if I have to complete squares, I will have to bring in this term. There's a quadratic term here. I mean, there appears to be a quadratic term here. So I'll try and get a norm of gradient fxt square. Obviously, I need to rescale, put a gamma square here. And is there any loss in putting this term? Gamma square gradient fxt square. No, that's also constant. As good or as bad as fxt. But the good thing is, with this I can complete the squares. And what is that squares? That is intuitive. Now we'll start looking at it. What is it saying? It is 1 upon 2 gamma the distance between x and the previous iterate. Square distance plus Cx. Okay. So maybe it's starting looking intuitive, and maybe you could have started with this also, right? So what am I doing? I'm just going to simplify this or make it look a little bit more intuitive. Uh, okay, so this is going to be 1 upon 2 gamma norm of x minus xt minus gamma gradient fxt norm square plus Cx. It's still a quadratic approximation. What is it saying? Well, if Cx, let's say there's some constraint. What is this saying? Well, I want an x which is within the constraint. If Cx is like an indicator function, then this will say x should be within the constraint such that the x is closest to xt minus gamma. This is xt plus 1, right? This was the supposed xt plus 1. Okay, so you can say this is the supposed xt plus 1. So it's basically saying give me an x which is closest to xt plus 1 modulo a constraint, modulo correction. So this is looking intuitive. Also, this update. The reason we are trying to connect it to the quadratic approximation is because that's when we'll get some of the convergence properties. So we want it to converge, we want it to look intuitive. Looks like this might serve both purposes. Okay. So we'll actually see. So question is, this is simplified formulation, but first order approximation around xt help. Help in the sense, can I actually start getting some nice, cute, for iterative steps, right? Yeah.
Why don't we decompose CX in its first order form?
Cx is first order form. See, Cx may not be, as I said, not differentiable. Na? Upper bound on the subgradient. You're saying basically, by the way, subgradient was not based on the first order, approximation, right? We just showed that if the function is differentiable, then the gradient which yields a first order approximation corresponds to subgradient. Subgradient otherwise is just a supporting hyperplane. Yeah, the thing is, it's still not very clear to me what your concrete proposal is. It's very intuitive. What you're trying to say is intuitively, can I do something with the way we got subgradient? Anyways, remember that subgradient will also have to deal with the hull. So there are other issues with subgradient besides, little lack of clarity. So it's not clear. Then you'll have to deal with this lot of indeterminacy, right? Which is subgradient. So, okay, so this is the idea. Gradient descent, which minimizes the approximation exactly as xt plus 1. I have now got in terms of proximity. So that's why it's called proximal. This is what makes it proximal. Okay, so hereafter I'll just replace this quadratic approximation with proximal. Okay, so proximal step plus Cx. Right, so again, if it had no C at all, it's business as usual. Gradient descent will minimize exactly this approximation. Okay. So now let's look at lasso. Okay, lasso basically when you're looking at phi x minus y plus lambda norm x1. We spent some time writing down the exact steps, right? You remember what was it? So let's try and write down. We'll try and illustrate on lasso. Write down this objective, argument over x of L2 norm phi x minus y norm square plus the lambda times the L1 norm of x. The L1 norm of x is not differentiable. That could be a Cx, yes. Yeah. Yeah. So when Cx is 0, the proximal step is a gradient step. That's it. Gradient descent step. So that is also a um, good indication that you are generalizing. That's why it's called generalized, right? Generalizing gradient descent. Can you write down the step? What would you do? First, you do a proximal. So you can write down the proximal step. What would the proximal step look like? It will basically mean you'll ignore the lambda norm x1 and xt plus 1 is, in fact, you can obtain a closed form solution. But let's write down, instead of a closed form solution, write it down. Write down the exact step. What will it look like?
Inverse y transpose y will be equal to x.
Right. What I'm saying that is if you set Cx to 0 outright. But let's write the gradient descent of the proximal step. I'm suggesting you write down the proximal step.
The proximal step is just computing the gradient of x small.
Yes. So don't jump into writing the closed form expression. See, one is to say, oh, Cx is set Cx to 0, write down closed form expression. No. Then you won't be dealing with, well, I mean, the quadratic approximation in some sense, you get for a quadratic expression like this, a quadratic approximation should be the original expression, but still I would suggest write it step by step. Because if you write a closed form expression, where is the minimization? You need an x variable, right? That's what we did. We still add an x. So just substitute. Substitute for gradient f of xt. Write down xt minus gamma times gradient f of xt. What does it amount to? And we are using a placeholder z. Instead of calling it the solution, we are saying z. This is not xt plus 1. Our new xt plus 1 will be after the proximal step. See, this was the supposed xt plus 1. But now what I'm doing is I'm calling the supposed xt plus 1 as z. That's all I've said in this slide. Because my real xt plus 1 will come only after proximal step. Right? Right. In normal gradient descent, you won't. I mean, in normal gradient descent, if you didn't have Cx, what is x that will minimize? I mean, which x will minimize is xt plus 1 only. This entire expression will minimize, right? So it's vacuous. I mean, Cx is what makes it look different. Otherwise, it will just turn out to be gradient descent. So please try and write down what will your z look like. Yes. So what is expression?
Just the xt minus gamma phi transpose phi x minus y.
Okay. Now what happens if you add a norm x? Sorry, one norm x plus lambda.
So we can take the subgradient, in which case we'll get the whole thing. If you want to make the whole entire subgradient.
But if you remember, we had derived at least one subgradient and one solution.
Yes.
What was that?
Cases for lambda.
Correct, right? So we can invoke that. So think about it. So, so my point is, if you just get that one subgradient, because you're looking for a sufficient condition. You just want a sufficient condition, right?
Oh, subgradient.
Yeah, subgradient set to 0.
Ah.
So can you set the subgradient to 0 for this new expression? See, for the original expression, setting subgradient is very challenging. You'll have to do a little bit of homework to convince yourself. Somebody may argue, why not just try and set the subgradient of this to 0? It's going to be difficult because it's going to have all these complex terms with respect to phi transpose. Whereas if I took the xt and then proximal plus c, the proximal step, right, which includes cx, and then tried minimizing this, right, with z supposed to be the gradient descent step on the first term f, you'll find that a subgradient solution, the necessary condition of subgradient going to 0, gives you actually a closed form solution, which is another very interesting reinforcement that we are on the right track. So while we don't get a closed form solution to the whole problem, we are able to do something meaningful with a sub problem. Is this clear? Yeah, minimization involves C of x. So there will be a subgradient. So let's look at the expression. Okay. So let's look at it.
Z minus x. Z minus x.
So it will become like this. You see here, we are looking at argument of a simpler expression. X, quadratic expression involving x with no matrix multiplication. Plus Cx, which is again, one norm of x. No matrix pre-multiplication on x. Here there is a matrix pre-multiplication on x. If you try and set the subgradient of this to 0, I mean, you can't. It's not easy. I mean, it's not possible. Like, finding subgradient is not going to be. Whereas this, you can easily come up with a subgradient. So it's not that we are not doing subgradient at all. We are simplifying the expression for which we need a sufficient condition check using subgradient going to 0. Okay, let's do that. You understand the spirit before we, huh? So can you repeat? So here what you're doing? Okay, let me just say. Here, instead of setting the subgradient of this to 0 in one shot, what are we doing? We are setting the subgradient of this to 0, the one in blue. We're setting the subgradient of this blue expression to 0 iteratively. Not once, iteratively. Every time z gets updated, I will again set the subgradient to 0. You understand the difference? Is that because otherwise we'll get lost in the math. That's why I'm spending more time before deriving. You understand the difference between the two expressions? Yes. One has a matrix multiplication on x. The other is a very plain x. If I get this z to be simply xt minus gamma gradient f of xt, then I should be able to solve easily. Okay. So this is the solution. What is the step 1? I'll do gradient descent for phi x minus y norm square, which is xt plus 1. That is what I asked you to derive. I hope you derive. Xt plus 1 is xt minus 2 gamma phi transpose phi xt minus phi transpose phi. Got it? Step 2, I'll set z to this xt plus 1. Whatever is xt plus 1. Okay, now for now, just assume xt plus 1 is set. So-called, suppose that xt plus 1. That's what I used to call there, right? Z is. Now you just have to solve this expression. This expression we have solved already. Prox gamma argmin over x, so 1 upon 2 gamma x minus z. Z is already set here. Square plus lambda norm x. What was the solution to this? Okay, just remember the solution to this. What was the solution to this part? Yes. What was the solution to this part? A sufficient condition. Using sufficient condition. Just 0 should belong to the subdifferential of the proximal function. Proximal plus Cx. That is 0 should belong to the subdifferential of 1 upon 2 gamma x minus z norm square plus norm of 1 norm of x. Oh, sorry, lambda times. So what is this? You get recap. We have done this. We have exactly this form we have solved. Yes, what is it? Xi. What were the three cases? Sorry? Z. Yeah, we'll have a little bit of 2 gamma lambda. This 2 gamma is also sitting here. Earlier it was just x minus z plus lambda. Now there will be a little bit of scalar. Huh? Lambda?
We get xi minus lambda xi.
Can I say xzi minus lambda gamma? The 2 will get cancelled out, right? Xi minus lambda gamma if zi greater than or equal to lambda gamma. Zi less than equal to, or less than, I think, less than minus lambda gamma and minus and lambda gamma, something like this. Right? That's it. So we wrote, right? Sufficient condition test for simplified lasso. You just need to plug it in. This is called ISTA, iterative soft thresholding. What's happening here? It is iterative. It is not one. This is the soft thresholding. This is soft thresholding. If Zi is greater than something, shrink it. Some less than something, increase it. Otherwise, clip it to 0. Soft thresholding. But what we are doing is iteratively. We'll get here. I've used the word W instead of Z, but otherwise it's the same. W or Y or whatever. Sorry, I've used W instead of X and Y instead of Z. And S lambda Y is yi minus lambda blah blah blah. This is the old notation.
What do you mean by iterative? So for one descent step of the algorithm, we do this small times.
One descent step you'll do once. And then you have to go back and do another descent. Because this has given you a new xi. So this, think of this as, this entire xi is t plus, right? Whereas this z was based on t. So based on t, I'll get a z, which I'll plug in to get xi for t plus 1. Clear? Okay. So this is clear, right? You just need to what do you call the sufficient condition step, plug it in, And now you should get more greedy. Okay, all this is fine. Can this converge? Right? We had so much convergence for the subgradient and all that, but can this converge? Can this converge faster than subgradient descent? There's no point in doing all this if it can't converge faster. And looks like, right? Because I mean, instead of subgradient descent, which would have just picked up one subgradient to descent, here we have found a sufficient condition for minimizing a proximal step, which is under a very, justified gradient descent approximation, right? Okay. So if you look at this, what is happening, right? Okay, this is just the proc step. I've just given it a new name. So instead of calling it xi, what I'm doing it is calling it a new name called prox. So what have I done? I'm saying xt plus 1 I is basically prox with respect to gamma. Remember, gamma was like our step size here. So step size based gamma prox of z. Z is basically a supposed xt plus 1. And if you want to call it, suppose you can also say prox of xt plus 1. That's also call it. Let's best is to call it prox of x tilde and intermediate x based on f, and then I get my final xt plus 1 ith component. It is clear? This is also I. So this is an ith component. Okay, so this gives us a final iterative soft thresholding algorithm for lasso. So now I've used W instead of, so imagine I was trying to minimize pi W minus y norm square plus lambda W1. So I want to write down the steps. The steps are exactly this. Wi t plus 1 is W hat t plus 1 minus, instead of hat, I've used instead of tilde, I've used a hat. Instead of tilde, I've just used a hat there. That's the intermediate one, minus lambda gamma. Now you've got the entire algorithm, right? It's called the iterative. So you see the iteration is only outside, not inside. Clear? Okay, so I've just repeated this thing, just recalling the subgradients and lasso sufficient. A little bit of repetition here.
So this is just some subgradient of the function phi x minus phi plus cx, which happens to be easy to apply.
Yeah, and which gives us sufficient condition. See, point is, if we can show that 0 is inside that, what is the problem? I mean, that's a very good subgradient, right? There is a subgradient which goes to 0. That's it. 0 should belong to that subdifferential. That's a sufficient condition. So in one sense, we are not computing subgradient. So remove this thought from, oh, we are again randomly computing. No, we are using the sufficient condition test for subgradients. That's it. Over the first one. This is the advantage we are getting. Yes, this is exactly the advantage we are getting. Well, this is the advantage you are getting for this specific lasso. But in general, so you may say, well, if I can't use a sufficient conditions test, is this less effective? No. Even then it is effective. So in this case, we are trying to create a good impression about, right? This is like a some little bit of advertisement for Proximal, right? And the ad works, right? But there is actual substance in this. It's not just advertisement, because what we are doing is, instead of finding a random subgradient for f of fx plus cx, even if I had to find a subgradient, I would do it for only the cx part. Use the gradient for fx and a subgradient after adding cx. It's still a better idea. Okay. Okay, so now we'll try, having seen one example, a concrete example, now we'll look at different classes. So gradient descent, we already saw is by setting Cx to 0. Okay, so we'll we all know it's proximal and blah blah blah. So Cx set to 0 is gradient descent. So having convinced you that this is good, I'm just going to trace all of this. On the other hand, the other extreme is proximal minimization. Let's say I have only constraint. I just want to find a feasible solution. Give me a point that lies within this space. Then I just set fx to 0 and minimize for cx. That's another extreme. We will not deal with that right now. That's a very nice other another extreme. Okay. So gradient descent implies this. Can I erase this or iterative soft thresholding? This is clear, right? Okay, so it's called proximal minimization. Now, projected gradient descent is when Cx is set to a sum of indicator functions, right? Which is what I tried to motivate in the beginning, right? And I project it and make sense. So this is what this is the example here is a summation. Instead of just one, I have a summation over multiple indicator functions, and this is called the projected gradient descent. So what about convergence, right? Okay, so I've illustrated projected here, right, as an intersection. So if you have C1, C2, it's basically an intersection of multiple constraints that we are seeking. Okay, let's look a little bit about convergence. What do you think? How, I mean, subgradient descent was order of 1 upon square root t. So if you get 1 upon square root t, we have wasted our time. If we apply subgradient descent to fx plus cx, we'll get order of 1 upon epsilon square, which is order of square root t. So can I do something better? Can I avail the regular gradient descent update and bring cx as an afterthought and get at least order of 1 upon t, not 1 upon square root t, right?
Even if just gradient descent to obtain one will be needed strong purpose. Or strong.
No, we could also balance with Lipschitz continuity. You remember the first book, Lipschitz continuity is all we needed, which is not difficult. We have seen Lipschitz continuity is fairly generic. So can we get to 1 upon t? And of course, can I do acceleration there? See, I can also apply acceleration here. But all that after getting 1 upon t, right? So the convergence result is as follows. If fx is convex, differentiable, and gradient of f is, f continuous with constant L. So as this f is differentiable continuous with constant L, and Cx is convex, you don't even need C to be Lipschitz continuous. But there is an assumption. Prox gamma z can be solved exactly like we did for ISTA. Prox gamma z, if you can see, somehow that's a black box. That prox, the projection, soft thresholding, somehow if you get a sufficient condition, check, and you can solve it exactly. Or you can solve it approximately, but that is a black box, someone else's headache. Not my headache, your headache. So if you take up the headache of solving prox, if it takes more time, that is your headache. Modulo that, then, right? So I just elaborated, right? What does it mean? In ISTA, for example, for lasso, you got a closed form sufficient condition using soft thresholding operator, right? So if assuming that that is taken care of as a constant, then f of xt minus f of x star, whatever, right, is upper bounded by x naught minus x star divided by 2 gamma t. What does it remind you of? Our first result. We were not super excited then, but it certainly was better than subgradient descent, right? I mean, how can we do better than that? I mean, we, right, we have already added too many more conditions that the prox can be solved exactly. C, we are not even insisting on Lipschitz continuity. Can't get more than what you got with F, right? It's basically what you would have got with F. Assuming the C part is taken care of through an exact prox step, right? So this proof is exactly like a gradient descent. I have written a footnote here. If we can't solve exactly, what do you do? We just treat this as another minimization problem and obtain an approximate solution. Modulo that. So you do a subgradient descent with respect to C if you can't solve it exactly. Okay, but still this is good. Right? We have this is out of the box thinking. Okay, so so there's also something called partial approximation minimization. I'll refer you to Bertsekas and Singh. Bertsekas is a very classic set of literature, including his book. So there's something called partial approximation minimization where you can still do better without a closed form solution. But we'll not get into that right now. Okay, so just to kind of contrast, put on record, for subgradient descent, we got order 1 upon square root t. For generalized gradient descent, it's order of 1 upon t. We have done better. And what has got us better? Because of assuming differentiability of f. Because subgradient did not even assume differentiability of f. And Lipschitz continuity of, sorry, this is Lipschitz continuity of f. Make that correction. Of course, you can know that good news is you can actually think of accelerated gradient descent here. What is the acceleration on? Acceleration will be only on this path. The gamma you can actually do Adam as well. So look at what we have got. We have got not just 1 upon t, but we've also got hold of many of the tools we have developed earlier. The learning rate you're trying to fix. You can also possibly talk about Lipschitz smoothness of f, right? So can we do even better without strong convexity for C, obviously, but can we do, say, better with strong convexity for F, and so on?
Accelerated steps here, we are saying that we do have a sense of momentum.
We can now have a sense of momentum on this Z part. The supposed, so momentum will be on availed on N plus 1 tilde, which is the same as Z, whatever, right? Sorry. Okay. Right, so exactly what I was trying to say. What do you do with accelerated gradient descent? Instead of prox gamma xt minus gamma, you will do a prox gamma of accelerated step. Right? And all the accelerated variants, including Adam, etc., you can evaluate here. other important point to say is, well, if Cx turns out to be a constraint, actually then in many constraint cases, unlike lasso, which was this is not a constraint, which was a one norm, in many constraint cases, you can actually solve it exactly also. So in many constraint cases, not just you can solve it exactly, but as you will see, there are some very interesting geometric interpretations of what we are able to solve, thanks to KKT conditions, right? So we'll talk about the Karush-Kuntakar conditions when we talk about projection. So it's opened up a lot of possibilities. That's what I'm trying to communicate. Okay. So projected gradient descent example, we'll see more of this, but one example is positivity constraint. Very standard. X should be greater than or equal to 0. Right? So if you write down, what will it turn out to be? It's very nice, right? I mean, if I see X is 0, if X is greater than or equal to 0 and is equal to infinity otherwise, which means it just starts speaking. Now, if you write down xt plus 1 or xt plus 1 tilde, if you want to call it, and then do a prox, you'll find that, well, this will just turn out to be clipping. If it's less than 0, clip it to 0. We said it's intuitive, and I said that's what seems to be happening, but you can actually verify this. This step is going to be what you'll get. Okay. There are some other, I already said there's a proximal minimization when you set fx to 0. I will not get into that more. Then there is, many other, I don't know whether we'll get time, but please do look at the previous year recording, maybe a couple of years back, where I talk about alternating direction method of multipliers, ADMM. All of that have their roots in this, the thread that we are discussing today. And we also saw lasso kind of special cases. So I'll give you all of this as extra optional material. You can certainly read. But our focus, since it's a little bit project last 2 years, I'm not covering those. Right. I talked about plain Lipschitz continuous can be slow for convergence. So can we do better for 1 upon epsilon square convergence? Yes, we can. We'll have to make some more assumptions. Right. That's also part of this. The assumption is the function that causes the non-differentiability should be simple. That Cx, see, so far we got away with saying, okay, Lipschitz continuity. But what if we want Lipschitz smoothness? We can. But that Cx cannot be too complex. So this is the formal proximal gradient descent algorithm. Okay, so this just putting the proximal gradient descent algorithm in perspective. This is the this is the key proximal descent algorithm. Okay, so so this is the other thing. If you can assume, this is we already saw. With Lipschitz continuity, we got 1 upon t, right? 1 upon t we got. Okay. So now the question is, how easy is it to compute the prox operator? We'll take some examples. A transpose X. I'll request you to do some of the homework. Otherwise, we'll not be able to cover much. So A transpose X. Very simple example. Cx is A transpose X. What do you think will happen? A transpose X is differentiable, right? So no fun. What about minus lambda log X? Is defined only when X is greater than 0. Is that interesting? Or Cx is mu X if X is greater than or equal to 0 or infinity otherwise. It's certainly more interesting. But even otherwise, let's take other example like Cx is a quadratic expression. What happens? See, that curiosity is important, right? Cx being a linear function may not be the right place to apply proximal, but we still want to know what does a proximal operator look like. Okay. The idea is to get a feel, right? So you just have to set this to zeros. Well, if it's differentiable, z minus x plus gamma c prime z should be equal to 0. The gradient, if it's differentiable. I mean, out of curiosity, you want to check what does it turn out to be. Right. Actually, a small note here. Some textbooks also have a slightly different definition of prox. They have this prox nu. They also put this 1/2 z minus x square and so on, right? So, yeah, I mean, so we had gamma, but they put something else there. So, okay. So I would like you to do this little bit of this as homework. Try computing the prox operator for lambda x cube, that is cx. Cx is 0 if for x not equal to 0 and minus lambda if x is equal to 0. So it becomes minus lambda for a specific point and otherwise it is just 0. The third is instead of minus lambda, it becomes plus lambda. Let's take the first example, right? So what is the proximal operator? X is r bin over x of x minus lambda square plus lambda indicator function of C. This indicator function of C is just x greater than or equal to 0. Basically, it's lambda x cube. Okay, so if you compute it, you will get this complex expression. 1 lambda minus 2 square root divided by 6 lambda if z greater than or equal to 0 and x is equal to 0 otherwise. So you try and verify it. So you just need to verify some of these homework problems, right? What the approach is for x greater than or equal to 0, you'll just take the dx, d by dx to be 0, which will give you this quadratic expression. 2x minus z plus 3 lambda x square should be equal to 0, which will give you this expression. Okay, I hope you can work this out yourself. Right, so, yeah, I think I'll just L1 norm we already seen, so I will not do this again. L1 norm is easy. Sorry, last time we already done, so it's a little bit of repetition. I brought up lambda. So this is an important table. Okay, so we did this, right? If it's lambda x cube x greater than or equal to 0 and infinity of x is less than 0, you get this expression. Well, how? Just by writing the quadratic expression and finding its roots. Let's look at some of the others. So this lambda x is greater than or equal to 0 is very much like lasso, right? It is just clipping z minus lambda. Simplified lasso is, of course, is basically saying absolute value of z minus lambda, right? The positive part of that into the sine of z. Right. So this part is basically a plus means max of 0 comma a. This part, the part in blue here, yeah, we derive this part, but this minus a lambda log x greater than 0 and infinity if x is less than or equal to 0 gives you actually a quadratic expression in z. And finally, if it's lambda x in a bound in an closed interval between 0 and alpha, then you get this very interesting min max. You get max of z minus alpha, clipping by shrinking z by lambda, right? Max of z minus lambda and 0. And then between the 2 and alpha, you're trying to, so this is intuitive. So what do you want? The moment you say there's a constraint like this, it should be less than alpha, right? But it is scaled by lambda. So in some sense, in the dual space, you are basically shrinking by lambda. So whenever you scale by lambda, it's like saying shrinking by lambda in the dual space. So there's a shrinking by lambda z minus lambda. And because there's a lower bound here 0, max of z1 is lambda comma 0. It can't go less than 0. Okay. So look at also how these are very intuitive. The same thing here, lambda x. Moment there's a lambda x, I'm shrinking by lambda. And then clipping it so that I look at the positive part because x should be greater than or equal to 0. But all of this you can derive, like we derived the third row. Okay, so some more operators here. If it's a constant, it'll be just z. If it's an affine A transpose x plus b, it is, as I said, anything that is being multiplied will be shrunk, will be used to shrink. So A transpose x will mean z minus A. Constant b will not matter, like constant c did not matter. Convex quadratic is interesting. Now, instead of pre-multiplying by a scalar or a vector, you are pre-multiplied or kind of multiplied by A. What you see here happening is exactly of this form. Instead of shrinking, right, because it's a quadratic expression, it's not linear. Right? This B transpose X will lead to shrinking by B, but this A is creating something called preconditioning. Your preconditioning, if the eigenvalues of A are large, then you're trying to shrink the eigenvalues of the resultant. Okay, so this is preconditioning based on the quadratic component. So just good to register what operations are happening, right? If there's an interval, then upper bound and lower bound give you max min. If it's a pre-multiplication by scalar, then that gets subtracted. If it's quadratic expression involving a matrix, then the inverse of the matrix will, the quadratic expression involving the matrix would have given a scaling effect corresponding to the eigenvalues. The solution as a result of proximal operation will have exactly the opposite effect, which is shrinking the eigenvalues through the preconditioning by A inverse. Okay. Now it's interesting. We don't just stop here. Maybe I should enlarge this a bit. How do I enlarge this? Okay, let me just. Can you see this clearly? So there's also calculus for the proximal operator. So what does it mean? Well, what if I had a C1 plus C2 plus C3 plus C4? What if I scaled the C's by lambdas? Right? What if I scaled the argument of C itself? Right? So all of these operations you see. So sum over component Cx, the first one. What is the calculus? So you remember we spent so much time doing calculus of subdifferentials, calculus of functions. We won't spend the time, but just look at the intuition. So moment you have a sum over components, it becomes a product. Product over the proximal operator. So Cx, prox of Cx, C, but now summation of C's will give you product of the prox. I mean, what? Again, intuition. What is an intuition? Prox can be, as I said, an indicator function. So if it's indicator, and if you take a sum of indicators, what does sum of indicators mean? Sum of multiple constraints means intersection, right? You want all of them to be satisfied. So product ensures that all of them are getting satisfied. The second is if you make a lambda x argument, I mean linear transformation of the argument, there's a simple scaling. So you will end up getting a lambda z, but after proximal based on lambda square. So if there's a lambda inside lambda square outside, and then you're subtracting the a after adding. So basically, you're doing a projection based on the additional component a, but you want to make sure you're finally independent of that a. So you subtract that a. Okay. The third is, so while a scalar inside persists, if you add a scalar outside, which is lambda c, then that reflects in prox of c by lambda. Right? In some sense, we saw that. Right? If you remember, we had that gamma 1 upon gamma plus 1 upon gamma to prox plus lambda times 1 norm. You had a lambda times 1 norm. You remember? Right? So that actually resulted in prox of c by lambda of 1 upon lambda z. Okay, so each of them can take a lot of time to discuss. What I've done is I've kind of also made some annotations here. Let me. So some of this we discussed. Look at this. So when you have Cx, to add to Cx, you're adding A transpose X, blah, blah, blah. So in addition to Cx, if you add these components, then there is some rescaling. And if you remember this, so this basically is a norm of x square. What is norm of x square? Norm of x square is nothing but x transpose Ix. So what happens with x transpose Ix? Yeah, I plus I, basically inverse, right? So you will have some preconditioning which we saw earlier. So here A is beta by 2i. A is beta by 2i. So therefore you have a, in the denominator B, beta. And so on. So I think all of this, you need to spend little time and argue for each of them separately. Okay. This is interesting. C norm of x. So here you're saying C. Okay, there's one more before the C ax plus b. Yeah, C x plus b is very similar to the C lambda x plus a. Some addition before proximal and then readjustment after prox. The last one was C of norm of x. So this is it's doing the prox on the norm of x but rescaling. So if you remember when we did matrix induced norms, so we had that rescaling, right? So the norm is basically saying, well, under the norm constraint, how does the prox behave? I think I'll. Okay. So these are not as interesting, honestly. I want to move a little fast to the projection part, which is more interesting. Right? This is, you can derive it. Some of them, as I said, are a little sanity check. So if a proximal point is, if f is 0, so we will not again spend time on that. So there is accelerated proximal gradient descent and its analysis by Beck and Tiblo to accelerate gradient descent. So what I'll do in the next few slides is just glimpse through what this accelerated proximal or accelerated generalized gradient descent does and its analysis, convergence analysis. Okay, so this is overall gradient descent. If you remember, you got this 1 upon 2t here. So what is the convergence rate for gradient descent and the corresponding accelerated version? Okay, so this is the only plot I'll discuss a little bit, and then the rest is just analysis, which is not going to be discussed, optional stuff. So when Nesterov's accelerating gradient descent gets applied even to the proximal case, you see that empirically the gains happen, right? So this gray is a subgradient. This red one is the generalized gradient. So generalized gradient descent, anyways, we know it's giving you a gain over subgradient, right? That's why we spend so much time to the proximal step, which is only applied post facto after doing the gradient descent on fx. But if you apply Nesterov acceleration, you can see there's still there's still more to be gained. Empirically, there's a lot to be gained. Okay, so what we do in the remaining few slides as extra optional reading material is actually show even with accelerated gradient descent, you can do better, right? What we had accelerated generalized gradient descent. I can do better than generalized gradient descent. The way accelerated gradient descent did better than gradient descent. Okay, so there's some extra and optional detailed slides. Okay, so I'm not. It's so complex. You're already seeing there's so much complexity coming with the proc step. On top of that, now you add a momentum term which is associated with your z or x tilde hat. It's just going to get hairy, and it is hairy. So for your eyes, right? What they look like, but it is after a point it becomes a little boring, right? So these are the actual derivation steps. Um, it gets even more colorful with too many terms that we need to memorize. You can see some very complex terms that come up here. The U is the unconstrained or unproximalized, right? So yeah, no, that's a Z. That's a Z. Yes. Okay. So this gives you 1 upon t. So this is the key. You get 1 upon t plus 1 t square, which is what we got using accelerated gradient descent. So this proof is there for you in case you're curious. Okay. So now we move to the last part. I mean, last part for this is a big part. I'll see how we can cover it. This is a projected gradient descent. I was really in a hurry to get here. So how will you solve for the prox operator in general for projected gradient descent when, let's say, I have some very complex set of constraints, right? Which is probably where proximal gets even more interesting. You can have non-differentiable Cx, but the big case for non-differentiability is constraints. So yeah, So the projected gradient descent, this is how you would visualize it, right? This is the constraint C. I'll end up going outside the constraint and projection should bring me back. Mostly I will land up projecting to some boundary point. That's how we would visualize it. So what would that entail? The steps are very simple. At each iteration, yt plus 1 is xt minus a gradient step. So yt plus 1 is this. Yeah, I'll annotate it here. This is yt plus 1. So xt to yt plus 1. And then from yt plus 1, I'll do a projection, right? The projection is nothing but the proximal step. So now we have a different view. We don't need the C. We are no longer talking about a C here. What are we talking about? It is argument over X in argument over X in C. This is how things have changed. That's what is happening, right? Take a normal from yt plus 1 or the Z or whatever and find the closest point in the constraint C. That is exactly the projection step. That is PCX. So so instead of calling it a proc step, we'll now give it a new name. It's a projection step, PCX. So now it is not PCXT. Just call it XT plus 1 tilde. Yeah, actually, to be consistent with the slides, I'll just call it PCY. Okay. Now the question is, when can I compute this projection in closed form? That is probably more interesting than all those proximal steps and proximal calculus, right? Okay. So there's a close connection between proximal and projected gradient descent. Exactly the connection I'm showing on the board. If Cx is indicator, then proxy is the PCX. So projected gradient descent is a special case of proximal gradient descent. I hope you see the connection. So the theoretical results, all results of standard gradient descent carry over to projected gradient descent as long as so the headache is still put on the projection step. As long as the projection operator is easy to compute. Somehow that has to be a black box. So that's the reason that projection deserves discussion. Right? Okay, otherwise it's exactly the same. We'll start with a previous projection x0p or xtp and then have an unprojected, right? xt minus 1p, you apply the gradient descent step and get an unprojected xut, then project xut to get xpt and so on. And you'll do this until some stopping criterion, the standard stopping criterion are met. Let's discuss that. So now I'm getting into the exciting part. What I'll have to do is I'll have to erase some part of the board. This needs a little discussion. So we are not interested in anything other than a constraint as of now. So what is a constraint? And we're going to start with a very simple constraint here. Okay, so our simple constraint min over x fx such that, okay, so what are we doing here? Such that g1x, there's only one g1, g1x is less than 0. Okay, let's take that less than equal to 0. So I'm going to take a very specific constraint. I mean, not too specific, then g1x less than equal to 0. So my objective function changes to, everything is the same. Argmin over g1x less than equal to 0. And for now, I will just, again, this gradient descent and all this is not so required. It's getting distractive for us. So this is some fx. Right? So it just happens to be a quadratic function here. Oh, wait. Sorry? Right? So for now, we'll further get to generalize and say, well, let's not look at this specific form, let's look at this form itself. So, or if you want, for now, just treat this entire thing as f. Just treat this entire thing as f because I don't want to get into a specific quadratic function here. How does this look for any function f? Okay. And let's understand this from the level curves. Right back, we'll look at geometric intuition first. So what's the intuition here? I have the gradient of f, which I'm trying to minimize. The gradient of f, and these are the level curves of f 10.5, 10.4. So you can see the gradient is in that direction, in the direction of increasing level curves. And it is perpendicular to the level curve. Okay. So I'm treating this f as 1/2 z minus x norm square is a specific example, but this analysis holds for any f. Look at the g1x. Now g1x also has its level curves, right? So I've said that this yellow shaded area, region is where g1x is less than 0, right? This region. Now, if the point where where f is minimized, we are interested in minimizing f such that g1x is less than equal to 0. So what are we saying? Well, saying if the point that minimizes f subject to g1x is less than equal to 0, happens to lie here, right? Let's say this is the point where it lies. Because this is a boundary, g1x is less than equal to 0. So it happens, let's say it lies on g1x equal to 0, the boundary. So there was a question earlier, right? Is it guaranteed to lie on the boundary of the constraint? Let's say it lies on the boundary. Then what's the necessary condition? Right? And then we'll also look at the case where it doesn't lie on the boundary. Then what's the necessary condition? Is that helpful? So there are two cases. So case one, is x star is on boundary of constraint. That is, in this case, g1x star is equal to 0. Okay. So then what do we expect between the gradient direction of f and the gradient direction of, actually I'm just calling it z instead of x. I've used the notation z there. I'll just, okay. I want to be consistent. Yeah. I'll use z. Okay. So if g1, if z is in the boundary, then what do we expect? Well, first of all, if I move in the direction of the gradient of g1, what will happen? I'll come out of the constraint, right? So I don't want to come out of the constraint. I'm on the boundary. If the gradient of f has a positive component along the negative of the gradient of g, then what happens? What does it mean? Saying gradient of f is minus proportional to minus lambda or minus of the gradient of g. At that point, what does that mean?
You can safely stay inside the constraint and yet attain a positive result.
Which means that if I go in the direction of gradient of f, which means if I increase the function, then I'll be landing up being within the constraint. I'm looking at minimizing, not maximizing. So that's good for me, which means if I move in the direction of negative of gradient of g, I'll only land up increasing the value of f. So this seems to be a desirable condition. So okay, if this happens, if xz is on boundary of constraint and g1z is 0, then necessary, I'm saying this is a necessary condition, that gradient of f as z is proportional to the gradient of g1, negative of the gradient of g1 at z. Okay, so I have given some textual interpretation. If the optimality point happens to be in the boundary, it means we cannot decrease g, which means honor the g constraint, while also decreasing f, which means, oh, I have not really found the optimal point. So I can't go inside g, be happy about g, and at the same time decrease f. So I'm putting this kind of constraint saying, no, you can't decrease f by going inside g. If you go inside g, you'll end up increasing f. Then I'm happy about being on the boundary. It was your question, right? Right? X is on the boundary of C, in which case gz equals C or 0 or whatever, and z minus x plus lambda gz is 0 in the case of f being a quadratic function, right? But let's look at the case 2. Case 2, what is case 2? What is case 2? Z is within the constraint. So then what is the necessary condition? See, earlier it was G1z is equal to 0 or C or whatever, and gradient f is in the opposite direction of gradient of G1. But if z is within the constraint, what should happen? What is necessary? Yes, G1 G1z is less than 0, and what else? You still want the z to minimize f. So gradient of fz is in the direction of what? Is it required at all? If I am in the interior of the set, why can't I just set the gradient of f to 0? I should not be able to move in any direction. In fact, if I'm in the interior, I should not be allowed to move in any direction around z and still increase the value of f or decrease the value of f. Right? So isn't the necessary condition that gradient of f of z is 0? Our favorite necessary condition is a necessary condition for minimum of a differentiable function. You get this? So yes, it can be in the interior, but in the interior, gradient of f should have gone to 0. Which typically doesn't happen if you're doing projection, right? Right? But yes, you're right. It doesn't have to lie on the boundary. So um, this is basically the condition. So what I want you to do as homework, think about it. This right? Optimality condition implies that gz equals c or 0 or whatever, I mean a constant, and z minus x plus lambda gradient gz is 0, which means that they are in different directions. The gradient of f, which is the gradient of z minus z norm square, right? I'm talking about this. This is my f. Though my study was in general, I'm now going back and saying, well, what does it imply? How can I get the projection operator? So with this necessary condition, just like I got the ISTA through a sufficiency condition, I'm now getting a necessary condition. Can I compute the necessary condition for projection? I mean, as a projection operation in all these cases. Gx is A transpose x, let's say less than or equal to 0. Gx is norm x square greater than or equal to some theta, whatever, right? I mean, some constant. Norm x1, some greater than or equal to some constant. Or less than or equal to some constant, sorry. So less than or equal to some constant, not greater than. Less than what makes sense. So if you take the first example, Gx is A transpose x. Then what will you get just by applying this rule as it is? Gz is C. It is A transpose x is C. And z minus x plus lambda A is equal to 0. If x is optimal point on boundary. So what will that mean? So that means you have to say that this x is z minus, so x is z plus lambda A. So either you have A transpose x is C and x is z plus lambda A, else x is equal to z, which means it's within the constraint. Okay, so I mean, I'm jumping here, so I'll post this table. You need to think about it. This is your homework problem. Think about it. How do you get these projection operations? Rn plus. This is most simple, right? Can I use the same rule which I talked about earlier, right? Inside and boundary to show that Rn plus, the projection is just the z plus. If any component of z is less than 0, clip it to 0. If it is greater than 0, leave it as it is. Box LU. What is box LU? Constraint says the component cannot be less than L and cannot be greater than U. Very intuitive projection. It's just taking the min of the max. You remember min of the max thing? I mean, it's just saying that if a component is less than U, make it U. If it's less than L, make it L. If it's greater than U, make it U. Box, that's it. can you show that these very intuitive constraints, actually, other constraints also intuitive may not be as straightforward. Can you try and get these as projection operations? Is this clear? We'll continue this next whenever we get the next chance. I know we have seminar presentations, but hopefully we'll get some more slots. So please think about this. How will these be? So this is the homework problem. All of these should come with a simple optimality condition. Gz equal to C and Z minus X plus lambda G's, lambda times gradient should go to 0. Yeah, Z is our, sorry, Z is X star here. Clear? Okay. We'll stop at this. Yeah, we'll resume presentations. Yeah, and whenever we get time, I'll continue this discussion.